So last class, the idea of the bootstrap is that instead of sampling, you have your data points, instead of taking them like a deck of cards and sampling them without replacement, where you take some subset of the sample that you have, so out of 101 data points, instead of dealing out some cards at random and having each card either 1 or 0 times, you can do it with replacement. So think of your data points as making a dice, and you roll the dice however many times you want to get more samples. And the idea is by doing this, you're going to do two things. Sometimes you will get one side more than once. So maybe you will roll the dice and you will get the sample point x2. Maybe x2 will appear more than once in your data set. If x2 appears more than once in your data set, that's fine. And some of them will be left out. And so by doing this, you get a whole bunch of different data sets that are all closely related to your original data set, but not quite exactly the same. And what is the point of this? The point is to then say, hey, if we have all these different data sets, we can understand the variability in anything we do. So for example, we can measure how much things change. We can see, if we run it again, would we get a very different result? Are things just random here, or are we really seeing something? So the reason this is useful is therefore can measure, I'm going to say significance in quote, significance. We can measure if the thing we're seeing in the data is really real or if it was just a fluke due to chance. And so if we run it again and we see the same thing no matter what, then maybe that's a sign that things are more significant. If we run it again and we see that it's we got something very different, then maybe that's a sign that there's a lot of randomness. So that is what we were doing last class. And we ended with this fact. This fact is that each individual point is included in the bootstrap sample, included in the bootstrap sample with probability. This is what we did right at the end. And what was the probability? Okay, let's say there were n points. Out of n points, the probability was 1 minus 1 over n. That was the chance that in any individual sample you don't include the point to the power n. So there's n chances. This is the probability to not be included. Point not included. In one sample. And then n is the number of samples. Okay, so so you're rolling this dice and you're saying, hey, what's the chance that I roll this dice and 2x2 never comes up? Well, in one individual roll, the chance of x2 not coming up is 1 minus 1 over n, right? If there were 100 points, it would be 99 out of 100. And then we do that 100 times the number of samples. So we roll the dice 100 times. So altogether, this is the probability of not being selected in one sample to the power n is not being selected in all the samples. This whole thing is the probability to not be selected at all. And so 1 minus this is the probability to be selected somewhere. Probability point is selected at least once. And that is 1 minus the probability it's never selected, which is that little power. So this is what we ended off with last class. And last class, we saw using Desmos that this is very close to, this is approximately 1 minus 1 over e. So there's e is the limit. This is like a math fact. E is the limit as n goes to infinity of 1 plus 1 over n to the n, and 1 over e is the limit as n goes to infinity of 1 minus 1 over n to the n. That is exactly what is appearing here. And 1 over e is approximately 2.7 ... 1 over e is approximately 37%. And so this is approximately 63%. Okay, so what does this mean? In our bootstrap sample, we have all our data points. And for every individual data point, there's a 63% chance it will be included in the bootstrap sample. And there is a 37% chance it is not included in our bootstrap sample. This is where we ended off with last class. So far, it's been all kind of a review. whirlwind review of last class and this little calculation at the end. Any questions or comments here about what's going on? What these things represent or why anything is the way it is? Okay, so now the question for you is we have this bootstrap sample. We have this idea of making our bootstrap sample, and we know approximately how many points are in, how many points are out. And so the question is, what could we do with the other points? So in our bootstrap sample, each point is included 63% of the time, and there are about 37 of the points that are left out. What is a good use of these leftover points? So we made our bootstrap sample. We have all these points left over. What could we do with them? So far, we've done nothing with them, but maybe you can think of something useful to do. Okay, I will let you think for a minute in the context of data science. What can we do with the leftover points? Again, it's a word cloud, so you can put in any weird idea that you want, and we will discuss them. Okay, who would like more time to think? Let me add a minute or two if people are still thinking. All right, 20 seconds, put in your ideas. Even if you don't have an idea, you could say, I don't know. Or if you, I don't know, you say add them in anyway. Whatever you think of. Okay. All right. What did people say? We should have a beautiful, beautiful word cloud here. Okay. Ooh, I like this. The big word is validation, right? And we had this idea of having a held out set of points as our test set. And before we were sort of doing that explicitly, but a lot of people are picking up on this idea that we can use any points that are not in our sample, we could use that as a validation set. Yes, some people even said out of bag. What could out of bag be? What is that? Let's see. Let's read some more submissions. Validation as one word. Okay. Yeah. So some people use for validation as a test set. Very nice. Oh, you could approximate E. Yeah, that's true. If you want to approximate E, you could do that. You can also just ask the computer for E. But yeah, that is a fun use for it. Okay. Left out points are best used as out of bag test data. So this phrase out of bag means exactly the thing that we're doing here. Is any point that you didn't use, you can then use as an error. Okay, so as a validation set to estimate the errors. So this is the new idea: is any points not included can be used as a validation set So in other words, going back up to what we did, deck of cards versus really big dice. In our first project, we said you have your sample points, split it up into a validation set of 20% and a training set of 80%, or however you split it, and then use the leftover points, the test set, as your validation set. Well, if you're doing bootstrapping, you roll the dice n times, and then whatever sides of the dice never came up, you can use those as your validation set. So you sort of get, like, by default, you get a validation set. And just because of the way the math works out, the validation set will be of size about 37%. So that's a nice trick. And the nice thing is you can do this many times. So instead of just doing it once, you can do it over and over again. You can do it as many times as you want. And because of the procedure that it's made with, you will always get a new sample, and you can figure it out. So it's like a version of cross-validation of using the bootstrapping and using this leftover set as a validation set. This validation set is sometimes called the out-of-bag set. So definition. This is called the out-of-bag. Out-of-bag. And the error you get, the error estimate is called the, quote, out-of-bag error. Okay, and just like you had the validation error is trying to estimate the true error, the out-of-bag error is just a kind of validation error made from this whole bootstrap game. Let me show you an example of this now. I have this whole shebang using the bootstrap and using this rolling the dice a bunch of times. I have it on linear regression. So the world's simplest example, here it is. So linear regression. So this should remind you a lot of when we did linear regression from before. So I have some true distribution, the population, and of course you don't know this in real life, you just collect the data. But then given some sample, I can make bootstrap samples. So let's see what these things look like. So the very first thing I've plotted here is this is the true population data. In real life, you only get one thing. And what am I doing here? Let me see. The standard deviation is 0.1. So I have 100 x values, and I want to plot their mean. And you can do the theory. You can resample it many times. And we know that the standard deviation is 0.1. We did this as an example in class. And so the confidence interval is of 95% confidence interval. 95% of the time, it's between negative 0.2 and plus 0.2, 2 standard deviations. And so the width of the confidence interval is 0.32. So that 392, or 0.4, very close to. So that's very nice. That's the theory, right? If you know the true distribution, you can work out the theory. If you don't know the true distribution, you can do Monte Carlo simulations. Here's 100,000 samples of the same distribution, and look, it's extremely close to the theory. So that's nice too. But in real life, of course, you can't know the real distribution. So this is like if you know the real distribution, you can do this. But in real life, you don't know the real distribution. You're given one data set, and that's all you have, but you can do this bootstrap. So I'm given one sample over here, and I bootstrapped it a bajillion times. So in my one sample, the sample mean of that one sample is 0.019, but then I bootstrapped it many times. So I took my one sample, which is 100 data points, and then I created, from my one sample, I created the really big dice, and then I rolled the dice, to make new samples. So it's sort of like a method to create an artificial new set, okay? And when you do that, you get this kind of plot. So in the bootstrap sample, sometimes the mean is a little bit higher, sometimes the mean is a little bit lower. And in this situation, 95% of the time, it was between negative 0.189 and 0.225. You'll notice this is a little bit larger than the true thing, right? The true thing was symmetric, minus 0.196 to 0.196. This one is a little bit shifted to the side, negative 0.189 to 0.225, which is not surprising because the true thing is mean 0 and our one sample is a little bit larger. So the whole thing is shifted over a bit, but the important thing is that the width is approximately right. So the width of the confidence interval is 0.4, and in real life, the width of the confidence interval is 0.4. So this whole bootstrap game is quite good for estimating the width. And this is the main use of the bootstrap. Okay, let's do an example now that's a little more complicated. I said that I was going to do linear regression. This was just x's. For linear regression, there's x's and y's. And so here is the kind of data that I have, right? I have this the x's and the y's, they're generated randomly, and they are close to this secret mean function. This is the blue function that we don't know, the true value that we're trying to get to. And of course, if you just take these 10 data points that were given and you do linear regression on them, you will get close to the blue line, but not exactly. So what is that? What does that look like? So there you go. The blue function is the secret mean, and then the red line is what you get by doing linear regression on these points. Beta hat 0 and beta hat 1, they're close to 2, 3, which is the true value, but not exactly 2, 3. Okay, and of course, if you had many samples, you could do it over and over again. Here's what, if you had 20 different samples, these are the lines you would get, and they're kind of like hover around the true value. And here it is in beta space. So beta hat 0 and beta hat 1, every teal point is a different sample, and you see they kind of hover around the true value, which is 2, 3. And by doing theory, we can calculate this box, and we think most of the time it should be near this box. This is all stuff we've done before. The new thing is to do it with the bootstrap. So here it is with the bootstrap. So if you only have one sample, so here's one sample, which I drew in red. This red line is the sample. And I can bootstrap that sample to get new samples, which are in teal. So sort of I can create these new data sets using the bootstrapping technique, and then I can run linear regression on each of those samples, and I can get all sorts of different lines. You'll notice occasionally you get something really weird, and you get some line that's like super different than all the other ones. That can happen. But what is the point is that, again, the same kind of principle works as before, is that you can, so this is the blue point is the true value we're looking for. The red point was the beta from our sample. And we can create all these other points by doing the bootstrap on our sample. And the idea is that you can get an idea of the width of this window by how spread out these points are. So instead of just saying, hey, I think the value is 2.1 and 2.4, you can get a plus minus. And say most of the time it was between 1.7 and 2.5. And most of the time this one was between 1.3 and 3.2. So that is the advantage of the bootstrap. And then last but not least is the new thing that we're doing now, which is to do the out-of-bag error. So that's what, whenever you see OOB, that is the out-of-bag error. And every single time we do an estimate, we get an estimate for the out-of-bag error, and that is supposed to approximate the true error. And the true error is somewhere around 0.7, and our out-of-bag error is kind of around 1, plus or minus a little bit. So the out-of-bag error is like our test error, and it kind of tells you an estimate for the true root mean squared error. Okay, so that's quite nice. All right, I think that is most of what I wanted to say about the bootstrap. Any questions or comments about the bootstrap or any of this stuff? Okay, so what is the next like level up of the bootstrap? If we've used it to calculate this how much things are changing. I think I wrote that down somewhere. We can measure how significant something is, how much things are changing. We can get error bars on all of our estimates by using these bootstrap samples. But there's one other thing we can do, which is called, this is the upgrade. We can do something called bootstrap aggregation. Bootstrap aggregation. And bootstrap aggregation is very long. It's a very long phrase. So people don't say bootstrap aggregation. They cross out all but the B over here, and they cross out all the ag over here, and they make a short form which is bagging. Bagging. So when people say bagging, they mean bootstrap aggregation. It's a very funny short form. What is bootstrap aggregation? The idea is combine the models from different bootstrap samples. Very simple idea. So as an example, remember, we have our data set. So let's call X data our data. We can convert our data set into bootstrap samples. So let's call that X boot 1 and X boot 2. In real life, we can do as many as we want, right? And the way we do that is we roll the dice. So, right, the data distribution makes our really big dice. We roll the dice however many times we want for our sample size, and that gives us the bootstrap samples xboot1 and xboot2. And then we can use these to model. So if we have x data and y data, let's add that on. We have the bootstrapped data in the x's and the y's. And then we can model. So we could do like e.g. let's do a model for each using the data, e.g. linear regression or something, and we get some function. So we get some estimate for f1 of x and f2 of x. And these are two different estimates from two different data sets, whatever model you want. So a good example is linear regression. And the idea is f1 and f2 will be very slightly different because these two data sets are very slightly different. So by getting two different data sets from our bootstrap, we get two different functions. And now we can combine them. That's what aggregation means. Aggregation means combine them. And we combine them by just doing the average. So f bag bootstrap aggregated, is the average of these two functions, f1 of x plus f2 of x. And the hope is we cross our fingers and we hope that the bagged function, f bag of x, is somehow going to be better than f1 or f2 individually. Let me give you an example. Let's see what happens if we do. Let's do it for linear regression. Okay. So when you do it for linear regression, f1 of x is actually a very simple function. It is beta hat 1 of x plus beta hat 0. And then f2 is going to be a similar thing with some different coefficients, beta hat 1 of x plus beta hat 0. And here is a nice thing. If you're averaging the functions and the functions are linear, then you might as well average the coefficients. So the f bag in this situation will be 1/2, and then you'll average the beta hat 1s, beta hat 1 plus beta hat 1. I guess let me add some superscripts. Which model did they come from? Times x plus 1/2 beta hat 0 plus beta hat 0. So for linear regression, when you average the functions, you might as well average the coefficients. So what this is saying in the example we just did, right? So we had, this is the true value we wanted, 3.2. We couldn't get that exactly. But from our one data set, which gave us this value in red, we got all these other values. And instead of taking this red value, we could just average all these teal values together. But in this situation, this doesn't do anything. So if you average all together the teal values, you do bootstrap aggregation on linear regression, then you are not getting much. You average these all together, and it will get back to the red point. So in this situation, bootstrap, very useful for finding the width of this interval. But if you're just doing bootstrap aggregation and averaging things, it doesn't do much. So this will be very approximately f1 of x, or f2 of x, or just the original f of x. So bootstrap aggregation for a linear model doesn't do anything. So conclusion. Does not do much. Okay, let's say for linear regression. Okay, and the reason is linear regression is linear. So when you're doing this aggregation of averaging the things, it's like it goes inside, and it's like as if you didn't do anything. And so bootstrap aggregation is only useful if the functions are nonlinear. So, so bagging is only useful for nonlinear functions. Okay. And in this situation, for nonlinear functions, it can be extremely useful. So the next example we're going to do is we're going to do bagging trees. We're going to bagging trees. Okay. And trees are very simple, but very nonlinear. So a tree is very simple, but very nonlinear. And so for the trees, the bootstrap aggregation will work and will make things a lot better. we're going to have to do a little detour here to understand what is a tree. I have a picture from the textbook. Hopefully you also saw all the videos. Here is a picture of a tree. So a tree somehow takes the space of x values, here's x1 and x2, and it splits it up into regions by asking questions. Here there's region 1, region 2, region 3, region 4, region 5. The way these questions are organized are in a tree. So first we say, is x1 less than or equal to some value? If it is, then is x2 less than or equal to some value? And then if it isn't, then we ask about x1 again, and we organize these yes or no questions, and that makes these regions in space. And then we assign a different y value to each of them. So the final function we get is very nonlinear and has these stepped surfaces. So it's almost like flat on different regions, whereas a linear function is like a big plane. This is a picture from the textbook. So this is what a final tree looks like. I will say these are binary trees, so maybe I'll write that down as well. These are binary trees. So we divide the input space using yes, no questions. So that's what makes it binary. And then we assign one single value to each region. Okay, so that is how we do the tree. A really good question is, how do we decide what question to ask? How do we decide what question to ask? Okay, and I think you probably actually already have an intuitive sense of what is a good way to ask these questions. And so I'm going to have you guys, we're going to do a very simple example with only x's and no y's. And we're going to create a binary tree that's going to help us figure out this. So here is a little fun problem we're going to do. We're going to create a binary tree to answer a question. And the question we're going to answer is based on this thing in my backpack, which I will now pull out. Let's see if I can find it. Ha 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 ha. The thing is a 20-sided dice. What number is on my dice? What number is on my 20-sided dice? Okay, and so basically the game is, I'm going to roll the dice. You're going to be allowed to ask me yes or no questions about the value on my dice. Yes or no questions create a binary tree. So the state space here are all the numbers, x going from 1 to 20. And we're going to divide this up into regions. And then your questions will divide this up into regions. And you want to try to make your tree as good as possible. You have to figure out what as good as possible means. And you have to figure out what the questions are. Let me put this in Mathematize. And I have this over here. Dice roll question. Okay, so I'm thinking of a number from 1 to 20 chosen by a fair dice roll. If you want to find my number in the minimum number of guesses, what is the best value to ask in this question? Is your number less than or equal to blank? Is your number less than or equal to blank? So I will let you think, how are you going to create this tree? And then we will do it. Okay. Let me give you 2 minutes here to think. Okay, 20 seconds left. All right, let's see what you said. This one should be not so hard. Okay, 15 people said 10. One person said 10.5. Here I said less than or equal to. So less than or equal to 10.5 and less than or equal to 10 are identical, because the answer is yes only if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there's 0 otherwise. So this one is correct. That one is what everyone said. What is the correct answer? The correct answer is, of course, 10. Very good. So if you've played like 20 questions, you kind of know this idea of we want to divide it into two spots. And so we have 11 to 20, and we have 1 to 10. And these are our two regions. And why did we pick 1 to 10? Well, we wanted to make them kind of the same kind of size. That turns out to be the optimal thing. To get even a little bit more specific, I'm going to make the question a little bit harder. Let's see if we can make the question a little bit harder. And here I have an uneven dice. So this time I'm thinking of a number from 1 to 20 chosen not according to one dice roll, but according to the triangular distribution. In the triangular distribution, the higher values are more likely and the lower values are less likely. The probability of each number is proportional to its value. So getting the number 20 is 4 times as likely as getting the number 5, because 20 is 4 times bigger than 5. This is the so-called triangular distribution. By the way, how can you make the triangular distribution in real life? You take not one 20-sided dice, but you reach into your backpack and pull out your second 20-sided dice. Let's do it. Here is my second 20-sided dice. And now if I roll both dice together and I take the maximum of these two numbers, that will be the number that is chosen, and the maximum of these two numbers will have the triangular distribution. So the bigger numbers are more likely, and the bigger they are, the more likely they are. Now the question is, if you want to find my number and the minimum number of guesses, now what is the best way to ask? So is your number less than or equal to blank? And this one is harder. Now the question is the same question as before, but now it's harder. You're going to need to work out with a pen and paper what you think it is. And I think I even gave you a list of potential values over here. So you have to figure out what I mean by this thing. Maybe for greater clarity, let me draw a picture of the triangular distribution so we can see. So this was question 1. This is question 2. Question 2. So now the dice roll, it looks like this. There's x equals 1, has some probability. X equals 20 has the biggest probability. X equals 10 is halfway. And the probabilities follow this nice triangle. So the probability that x equals some lowercase x, it is the function x divided by some big constant. I guess what should the big constant be? It should be a 1 plus 2 plus 3 plus 4 all the way up to 20, which I guess is, what is 1 plus 2 plus 3 plus 4 all the way up to 20? It's 110. 20 times 21 divided by 2, 210. Okay, good. So the probability that any number is chosen is x over 210. I think that's right. Yeah, 20 times 21 over 2. Okay, so the probability of any individual number is proportional to the number. There you go. And now the question is, what is the best value? What is the best value to put in our tree question? Okay, so we're gonna, in other words, we're still splitting the same space, but now x equals 1 to x equals 20 are not all equally likely. And I gave you some options, I think. So it is a multiple choice question. You can check out the options and try to work it out. Let me give you, this one's trickier. Let me give you 3 minutes, and you're definitely gonna have to use a pen and paper to work out what's going on here. All right, there's 40 seconds left. Even if you have not finished, make sure you put in a guess by the time we get to the end, and then we're going to discuss the guesses and see if there's a clear consensus or if people are split on what to do. Okay, let's take a look. Again, this one is quite a bit harder than the first one. The first one, I think lots of people can sort of intuitively get the right answer in a number of ways. But this one, people are quite split. So 12 people are in 20 times 1 over square root of 2, and 8 people are in 20 times 2/3. Only one person went for the exact midpoint, 20 times a half. That's what we had before. And that one is wrong. So it is actually one of these two things. These two things are respectively the mean and the median of this random variable. So this is the fact that we're going to use. If you look at this triangular distribution, the mean of x is 2/3. How did I get 2/3? Well, it's some kind of 2/3 times 20. In this case, 2/3 times 20, you sort of can do the integral or a sum, if you want, of the function x over 210. And when you integrate the function x times x. Okay, great. Let me start over. So this is approximately, it should be a sum, but it's approximately this integral of x times the probability x equals x dx. So you end up integrating 0 to 20 x times x. You end up integrating x squared, and the integral of x squared is where this 2/3 comes from. So for people who know calculus, this is 2/3. I'm skipping a bunch of steps here just to give you the vibes. 2/3 times 20. That is the average of this random variable. On average, when you roll 2 dice and take the average, you don't get 10, you get 2/3 times 20, also known as 13.33333. On the other hand, the median is a little bit different. The median, and this one is 1 over square root of 2 times 20. What is 1 over square root of 2 these days? Let's get the computer to do it so I don't say what the wrong value is. So let's see. 1 over square root of 2 times 20 equals 14.14. Very nice. 14.14. This one is 13.333. Why is this the median? Well, the whole point is to look at the cumulative distribution function of x, which is the probability that x is less than or equal to x. And this one grows like x squared. So this is like x squared times something, maybe 1 over 420. So this is growing sort of quadratically. If the probabilities grow linearly, then the cumulative probability is the sum of these things, or the integral of these things. It will grow quadratically, like x squared, and therefore the median is the point where the CDF equals a half. The CDF of x, let's call it x star, equals 1/2. The median x star is this point. And so you solve, you're going to get an equation that's like x star squared equals 1/2, and therefore x star equals 1/2. Okay, again, I'm leaving out the 1 over square root of 2. I'm leaving out the 20s. So there's some steps. There's some steps missing, but that's essentially where it comes from. So when you do the cumulative, you get an x squared, and you take the median, and you are solving x squared equals 1/2. When you do the mean, you're just averaging, you're integrating it. So you integrate up this x squared to get this 2/3. And that is where the difference between the mean and the median comes from. In this problem, the median is a smidge higher than the mean. The median is like 14, whereas the mean is like 13. All right, great. Those are the two options. Now the question is, which one do we actually want? We don't want any of this. We want, where did my thing go? We have lost the thing. Let's show windows. And where are the windows? Not this one. 1 over square root of 2 times 20. This is it. Okay, great. Okay. So which option is right? Is it the mean or is it the median? So remember the definition of the mean, the average, and the definition of the median. There are two different things. Which one do we want here? And now that we've sorted out which one is which, I will let you revote, and you can pick between the median and the mean. This one is the mean. This one is the median. Which one should we be picking? That's a great question. Okay, I will revote it. So I'm going to open it up one more time, and you can put in what you think is the right answer. So dice roll, we did, and I'm going to duplicate uneven dice rolls, part 2. Okay, so I will let you choose again. This time you know what you're doing. We've done this sort of calculation. Let me give you 1 minute to do it. Okay, let's take a look. Did people go with the mean or the median? This time people have moved. I think this one had a very, very slight majority before, and it has a pretty substantial majority. We've seen many cases where the majority is wrong, but in this case, the majority is right. It is the median. And so the nice thing about the median is it splits the whole shebang, it splits the whole space into 50-50. So this is x star equals the median. And the median has the property that everything to the left and everything to the right have equal probability. So the probability of being over here is 50%, and the probability of being over there is also 50%. I guess in this situation, it's not going to work out exactly because it's going to be approximately the median, not exactly the median. You're going to say 14 and not 14.333. Yeah, so this is the probability x is here is approximately 50%, and the probability x is here is also approximately 50%. What was the whole point of this exercise was to try to get you to realize this is how the decisions are made in trees. You choose a criteria that is meaningful to you. In this case, trying to make them as balanced as possible, 50% and 50%. That leads to the fewest number of questions. And then you just add in questions according to that thing. So if we were going to have another layer of questions, once we've split it up 50 and 50, we would again try to split it up into 25, 25. So the next question would be somewhere over here, and it would be again a 1 over root 2, where this area would be 25%, and this area would be 25%. And over here, it's going to look a little bit different. Here, it's going to be pretty close to the middle. But it's still, again, 25% and 25%. So what is the moral of the story is that to create a tree, you just decide on what you want your tree to do, and then you just choose where the optimal spot to do it. So this is called creating a tree, and indeed, you can do it greedily with respect to some function. So creating a tree, you choose a criteria, e.g., minimize difference of probabilities. So if you minimize the difference of the probabilities, then they will be as close to 50% each as you can. And then choose the point that does that. Choose the question that does that. Okay. And depending on what you're doing, you might choose slightly different criteria. A good example is for a regression tree. So suppose you are doing a tree for regression. So you have a bunch of x's and y's, and here's an example. The y's are real numbers, like suppose they are the housing data set, where the x's are information about the house and y is the price. What would we want to minimize? The criteria in each step could be the minimize the RMSE of that region. Minimize the RMSE of each region. So in other words, if you had a bunch of, if you had X1 and X2, and then you have a bunch of different houses that are sort of spread out throughout, and maybe there's some expensive houses and some cheap houses and some middle-priced houses, you would try to find a region to divide this up into, so you try to group together all the houses that are the same price to minimize their RMSE. So maybe something like this, that would be a thing to do. So I guess we have to ask on X1, and maybe this region has all the houses here have a very similar price, so the RMSE is very small. All the houses over here have a very similar price, so the RMSE is very small. And so this would be our decision boundary is here. So we say, is X1 less than or equal to this T1 value? And if you do this again and again and again, then you will end up exactly with the kind of thing that we saw over here. So going back to the textbook example of a picture of a tree, this is how we decided on these questions. These questions are set up so that in every single region, the RMSE of the data points inside the regions are as small as they possibly can be. And by making them as small as they possibly can be, that means we've grouped together things that have a very similar value. And this is just like you were doing with the dice rolls, except instead of trying to make the probabilities as close to 50% as possible, you are trying to minimize the RMSE. So just having this notion of what you're trying to do, that is how the questions are created. Of course, to do this, you have to do it for one level and then another level. And one way you could think ahead and think of all the divisions, but usually we just do the greedy algorithm. So let me say a word about the greedy algorithm. So that's what we want to do. And we normally do this greedily. So greedy means do question 1 first, best as you can, then just repeat. Then repeat for further sub questions. Okay, and why is this greedy? It's because we're doing question 1 as best as we can without thinking about whether or not what we did in question 1 will make the further questions harder or easier. We just do our best in question 1 and then we keep going. We never backtrack and say, hey, actually what we did in question 1 was a bad idea, because question 2 was really hard. So that's what makes it greedy, is we just do one question at a time. And very often, like for a regression, we'll just do greedy trees with the RMSE, and that is how the tree is created. And so once again, I think the pictures in the textbook are quite nice. Is you have some data set, and you say, like, what would be the T1 value that would make the RMSE of the two groups as small as possible? Oh, it's this T1. And then amongst those two groups, what would be the best question I can ask to make the RMSE as small again? Well, in this case, it's X2 is less or equal to T2. And so you try a bunch of different values. You take the one with the minimum RMSE, and that is how these trees are created little by little. Okay. What is the point of all this? Well, you should understand how the trees work. Of course, in practice, the computer will do it all for you, and it will automatically do all these things, but it is up to you what you want to specify. So if you go into the options for the tree, you can say RMSE, you could say something else. So you could do RMSE, you could do another criteria, and in fact, for classification trees, another example. What if it's a classification tree? And in a classification tree, there are not Y values, there are different categories. So there's, I'll call it X, and C for which class they are in. And instead of doing the RMSE, I could minimize the entropy. Minimize the entropy, that is one possibility. or another thing, some people call this the Gini index. And both of these things are measuring how different the classes are. So you want to have a situation where after you ask a question, what is left over is all very similar classes. And I will give you an example of this for a classification tree. I have a nice example here of a data set of penguins where I have done this. So here is what I call the penguin classifier. And this is a data set of different penguins. And there are 3 types of penguins. One of the types of penguins is an Adelaide penguin. And we measured the different sizes of the penguin, how much they weigh, how long their flippers are, how big is their bill, and we're going to try to use these to classify the penguins. What are the 3 types of penguins? There's Adelaide, and I think there's also Gen 2, and what was the 3rd type? Yeah, here we go. Chinstrap. These are the 3 types of penguins. So there's 41% of my data set is these Adelaide penguins, 20% is these chinstrap penguins, and 36% are these Gen 2 penguins. And we want to ask simple questions about the penguins to try to classify them. And our tree, what it is doing, it is trying to ask questions to maximize in the subgroups how different they are. So in fact, the first question my tree asks is the flipper length in millimeters greater than 207.5 millimeters? And if the answer is yes, there are 91 penguins that have a flipper length longer than 207, but in those 91 penguins, almost all of them are Gen 2 penguins. So in other words, by asking this question, we have taken the distribution, which was almost evenly split, or like a nice mix of all 3 types of penguins, and we have made it just one type of penguin. So the entropy of this distribution is very low. We're trying to minimize the entropy, and this is what it does, is it kind of splits them up like this. Of course, the other side of the equation here, the bill length, is now it's split by these 2 types, the red type, the Adelaide penguin and the Chinstrap penguin. So we ask another question, is the bill length greater than 44.7? And now we have almost perfectly classified it. 48 and 104 here. So we have almost perfectly classified the penguins just based on these 2 very simple questions. What is their flipper length and their bill length? And this is all done automatically by a CART learner. CART stands for categorical something. I don't remember the rest. But all of this is done automatically. So you don't have to worry about how these things are done. You can tell it what you want to do, but it will do it automatically for you. Okay, so that is a tree and how a tree works, and a nice example. So both of these ideas are make the distribution as one type as possible. Okay. Okay, so those are the basics of the trees. The next thing we're going to do is we're going to combine the trees. The trees by themselves are kind of boring, but this is a great place to pause for a moment. Are there any questions about how the trees are made or what the tree is doing? So I should have done, instead of the dice, I should have had you guys do penguins. I should have said, what question should we ask about the penguins to make them as different as possible? So here is the downside of the trees. There are a lot of upsides. One is it's quite nice. You know, we have these nice questions. Like if we had some guy in Antarctica who was measuring penguins, we could say, first measure their flipper, then measure their bill. You know, like we can have some nice questions. But I'll tell you one downside of the trees is they are not great. An individual tree is kind of a bad model. And here is one way you can tell it's kind of a bad model. Its training accuracy was 96%, so 4% error. But its test accuracy on the test group was only 92%, so like 8% error. So basically, it's overfitting by a factor of 2. The training error is twice as good as the test error, and they are overfitting. So the trees on their own are, they have pros and cons, but they're not great. So trees on their own. On their own, pro, easy to interpret, but con, they tend to overfit. Overfit, and not very powerful. Okay, and this is, why on earth am I telling you about trees then, if they're so crappy? Who would use a tree? A tree on its own is not great, but a tree makes up part of something called a forest. And a forest is a collection of trees, just like in real life. And even though a tree on its own is quite bad, a forest can can be quite good. And so this will have all the pros of the, each individual tree will be easy to interpret, but the pro is that it will be very performant, can be highly performant. So we can fix this problem. I will say you do kind of give up a con, because even though each individual tree is possible to interpret, if you have like 1,000 trees and you're saying, I'm doing all these trees, every individual tree is easy to interpret, the poor biologist in Antarctica will have to measure a different thing for every individual tree. So not as easy to interpret anymore. But they are very good in terms of performance. Okay, so let's see. What is a forest? It's a collection of trees. What does it mean to combine them? Well, we did this. This is where we started the class. The way you combine them is you bag them. You do this bootstrap aggregation. So instead of doing one tree, what you do is you split your data set into multiple pieces using the bootstrap method. You take your collection of penguins or whatever else, you create several different bootstrap data sets, and then the model, don't use a linear regression model, use a tree. And if you use various trees and then add them all together, the hope is that the bagged tree at the end, which is the bagging individual trees, will give you something called a random forest, and that will be highly performant. So that's the idea. Let's write it down. How to combine them. Method. Use bootstrapping to create many data sets, data samples, and one tree per sample. So by the bootstrapping method, we can create these various data sets. And because they're bootstrapped, they are not exactly the same. They're all slightly different. And trees are very fickle. So if you have a very slightly different data set, you might get a completely different tree. And that's actually a good thing in this situation. The trees are very different. The trees you'll get from this thing, even though they all came from the same original data source, because they were bootstrapped to different samples, you get different trees. And then we combine them by averaging. Average them all together. And when you average them all together, so you get this F, which is called the random forest of X. That is the average over the number of samples you did. Let's call them bootstrap samples. The number of times you did the bootstrapping procedure, then you just average them all up. And boot samples. And then you do F of tree number I. And because these are all trained on different sets, they're all on a slightly different data set, all these trees are slightly different, and so when you average them up, it's better than any individual tree. So this is the so-called wisdom of the crowds. The wisdom of the crowds. And the idea is, even though every individual tree is sort of crappy, the average of all the trees can be quite good. The average of many poor estimates, let's say poor estimates is better than the average of any individual one. So even though each individual tree is not great, averaging together many trees can be quite strong, which is kind of surprising. I will say it's very important that you bootstrap, right? If we didn't have the bootstrapping, it's important that these are different. Maybe I should, this is a key word that I forgot here. Many different poor estimators. If you just average the same thing over and over again, of course you're not going to get any meaningful improvement. The fact that these are bootstrapped is absolutely key to this method, because it means that the trees are all pretty different. And when the trees are different, then we can sort of get this wisdom of the crowds benefit, where even though every individual tree is kind of wrong, when we average them together, they get a little bit better. And I have some examples. So let's go to the penguins. Oh, look here, I did put some of the hyperparameters in here. Okay, what was this? I made the number of examples. Okay, well, never mind. Let's skip back. Let's go to the random forest. So in the random forest, again, it is all built in. I said a random forest learner. and that will automatically do what I just said. It'll automatically take the data set, the training data set, it will split it up into these bootstrap things, and then it will train many trees on each of them and figure it out. And in this case, not only did the accuracy improve by quite a lot, so even though it's the same examples as before, and before, what was on a single tree, it was 95.5% accurate. On the random forest, the accuracy is 99.3, so extremely accurate. We went from a 4% error to a 0.7% error. That's a huge improvement by like a factor of 4. And not only that, is the test accuracy is a lot closer to the training accuracy. So the random forest is a really like top tier model, and it was made from a crappy model, which is I think is like a cool thing, that the way you get to your good model is you take a bunch of crappy models and combine them. So there you go. That's an example of it working on the penguins. There's also a nice picture I have from the Google. This is the Google Machine Learning Developers course, where they talk about random trees, and they have some nice things, and they have a picture over here. So here is a nice picture of why, another way to think about why forests are better than trees. So imagine that the truth is that there's two regions, so imagine x1 and x2 are the two axes here. And there's two classes, there's the red class and the blue class. And the truth is that there's some kind of circle going on. Well, the problem with circles is trees can only ever do axis-aligned questions. They can only ask about x1 or x2. They can only do vertical or horizontal cuts. So any individual tree, the best it could do is some kind of weird rectangle shape like this. So the best kind of tree you can get, this is a pruned tree, so it's like a tree that has been improved by doing some pruning, but it's still kind of crappy because it's still got all these jagged corners. So every individual tree cannot, really because it's a tree, cannot get that close to the truth. But if you average many trees, that's what a random forest is, you train many of these trees, then on average you get a much better fit to the circle. You get these regions by averaging together many jagged things, you get together something that's a little more smooth. This is also how your computer works, right? Like it's got a lot of pixels. The more pixels you have, the more you can approximate things like that. So every individual tree is kind of blocky, but the average of many trees can match these kinds of things. So that's another way to think about why random forests are quite nice. Okay. There is one other thing I didn't mention. Let me mention that now, which is we do bootstrap on the samples. We also sometimes do bootstrap on the features. Also bootstrap the features. Also bootstrap the features. So in addition to every individual tree being trained on a different set of X values, it's also trained on a different set of features. And what do I mean by this? There's a nice picture in the Google developers course. I think if I go up a bit, it'll be here. Yeah, here it is. So this is called attribute sampling. And what we do is when we look at our tree, maybe our individual points have 5 attributes, F1, F2, F3, F4, F5. When we make our tree, we say this tree is only allowed to look at a certain subset of these samples. This tree in particular could only look at, I think, what was it? F2, 3, 4, and 5, or something like that. Here is the decision tree trained with 5 features. The blue nodes correspond to the tested feature, while the white ones are not tested. So you are not allowed to look at F1 and F3 for making this tree. And you might say, hey, wait a second, this is making the trees really crappy. You've made the trees worse. So i.e., leave out certain features. In the context of your housing data set, this would be like, let's just ignore the lot area or something, right? Like we're going to ignore certain features. Of course, ignoring features makes your trees worse. This, looking at the features, bootstrapping the features, or doing feature selection at random, this is at random. This is a totally dumb idea. This makes your trees worse. But however, it makes every individual tree worse, but it makes your trees more different. And this is the secret. So even though this thing with the features, it makes them worse, it makes them more different, and then when you average them together, you can get a better improvement. So this is the kind of thing that you can do with trees. These are some of the hyperparameters you can do. There are many hyperparameters. And this is part of the reason trees and forests are really good, is there's a lot of different things you can tune. You can tune the depth of the tree, of the trees. You can choose the function to minimize. You can do the how many features to use per tree, how many features per tree. And so by tuning all these different hyperparameters, you can usually find a good model. I will say one nice thing is that the number of trees always seems to help. The more trees you put in a forest usually helps. More is usually better. So it is not one of those things where you have to worry about overfitting, because when you add in more and more, somehow they don't overfit. You're adding in more different things, it gets better. And Google also has a nice little plot for this idea right here at the bottom. So this is a plot of the number of trees. Let's see if I can make it a bit bigger. The number of trees versus the accuracy. Hey, look, it says accuracy out of bad. They're measuring using the out of bad. That's what we started the class with. And the more trees you put in, it sort of doesn't overfit. Because the trees are all sort of independent, or as different as you can make them, adding more trees does not tend to make performance worse. That's another nice feature of these random forest models. Okay, I think that's mostly what I wanted to say about random trees and random forests. If you would like to use random trees and random forests for your project too, you are more than welcome to. Again, you got to be careful with tuning the parameters. We got to figure out what all the different parameters mean in whatever package you're using, but it's a totally valid way to do it, in addition to the classification methods we learned earlier in the course. Any questions or comments about trees or forests? Yeah?
So for the bootstrapping the features, are you doing replacement?
I think, so it depends on exactly what they're doing. But often what they do, let's go to this picture. It depends on the individual package you're using. Sometimes they will delete them for the entire tree. Sometimes they will delete them for only a question. So they'll say every individual question, we just randomly choose what features you're allowed to use for that question. So in this example, they said, in the first question, you can ask about F2, F4, or F5, but not F1 or F3. But in the second question, we just resampled it. And we said you can use F3 or F4, but not F1, F2, or F5, right? And sometimes they'll do one for the whole thing, which is nice for in your code. You'll just say what the features are at the beginning, and then do it. In other ones, they'll do it per question, so it depends on who you do. Sometimes they're done with replacement, sometimes they're done without replacement. You have to look at the details. Yeah, that's a great question. Okay, any other questions or comments? All right, let's stop there. We'll see everybody on Monday, where we're going to start regularization. There's a really fun video in the pre-class videos that you should watch about the weirdness of this regularization stuff and why it works. But we'll see everyone on Monday.